In part 2 of our study on rational functions, we will explore vertical asymptotes and wholes. They are related in a sense that they are both values that make our denominator 0, but they are different in how we can algebraically factor and cancel our rational function. So if you take a look at this big picture here, we have a vertical asymptote where x equals 3, and a vertical asymptote just means that our function approaches either negative or positive infinity as it approaches the vertical asymptote. So the way that we would talk about this vertical asymptote is that if we called this function f of x, we could write this in a really cool calculus way, and we could say as x approaches 3, now, from which side? Let's first talk about approaching 3 from the left-hand side, so talking about this part of f of x. So as x approaches 3 from the left, what does our function do? Our function f of x is going down towards negative infinity. And then as we approach 3 from the right, so as we're approaching x equals 3 from the right-hand side, we can see that f of x is going up towards positive infinity, which is pretty cool. So that's a vertical asymptote. It's when our rational function approaches either positive and or negative infinity on either side of the vertical asymptote. So 3 clearly makes the denominator 0. We can't see the function's equation, but we know that x equals 3 would make the denominator 0. We have something called a removable discontinuity, or a whole, they are the same thing, when x equals negative 1. X equals negative 1 also makes this function's equation, it makes the denominator equal 0 as well. However, it's something different, and we'll explore that in just a moment here, in that the factor would end up canceling from top to bottom, and that's why it's not a vertical asymptote. It is a whole or a removable discontinuity. This is a more calculus definition of what this is, and in pre-calculus we just simply call it a whole. Now, it's important to note that wholes are so infinitesimally small that your graphing utility and or Desmos is not going to show you the whole. If you were to plug in -1, it would say there's an error because there's really not anything there. However, you're not going to be able to see a whole on Desmos or your graphing calculator. So that's why it's important that we can identify them algebraically. In our next picture here, this was just an example I found online. We have a rational function. It's been factored in the numerator and the denominator. We can clearly see that the values x equals -1 and x equals positive 3 are restricted in our domain because they both make the denominator 0. However, they look very different on our graph. If we take a look at when x is -1, we see that there is a vertical asymptote there. Our function approaches positive infinity and negative infinity as x approaches -1. And that's why we have a vertical asymptote there. It makes our graph look wonky there. But how come there's not a vertical asymptote when x is 3 if it also makes the denominator 0? Well, we can clearly see that this factor up here, x minus 3, can cancel top to bottom. Therefore, when x is 3, we have a hole in our graph instead of a vertical asymptote. So that's the difference. Now, how did they find this value of 1/4? Well, after they canceled the x minus 3's, they were left with x minus 2 and x plus 1. And what we can do is we can then plug in that value of 3 into our new function that's been canceled, and we do 3 minus 2 over 3 plus 1, which will end up working and giving us 1/4. So even though that value is not technically part of our function, we can tell where the whole is and what it would be by plugging it in once we've canceled the issues. So that's the difference between a vertical asymptote and a whole, in that they're values that both make our denominator 0, but a whole happens when we can cancel those factors top to bottom. These right here are just the intercepts, the x and y intercepts, and we'll talk about a horizontal asymptote in the next video. For these two examples here, we want to identify any vertical asymptotes and wholes in each rational function. So what we need to do is factor both the numerator and the denominator. I'm going to do them in different colors. I'm going to work with the numerator in black, and I'll do the denominator in white in just a moment. So let's take a look at the numerator. The numerator, we can take out the GCF of 2, and so we're left with 2 times 2x minus 1. What's left inside here is not factorable, so we're done with the numerator. That one was pretty easy. Our denominator is not quite as simple. This one, I decided to put it on here because I think it's a good example, and actually white's a little bit hard to see, so let's do yellow instead. So in the denominator, we have a quadratic trinomial, 2x squared plus 5x minus 3. And when we multiply a times c, since there's no GCF to initially factor out, we can multiply 2 times negative 3 and get negative 6. So we need two numbers that multiply to negative 6 that add to our b value of 5. Those two values are going to be a positive 6 and a negative 1. And so we'll rewrite the denominator as 4 terms, 2x squared plus that 6x minus the 1x minus the 3. Then we'll factor by grouping. So the GCF of the first two terms is 2x, and we're left with x plus 3. The GCF of the second two terms is minus 1, and we're left again with x plus 3. So this will factor into the terms on the outside, 2x minus 1, and the terms on the inside of the parentheses, x plus 3. All right, rewriting with our new numerator and denominator both factored. Our numerator is 2 times the quantity 2x minus 1. And our denominator is 2x minus 1 and x plus 3. Now we can clearly see that there are two values that will make our denominator 0, x equals 1/2 and x equals negative 3. Now the x equals 1/2, that comes from a factor that can cancel top to bottom. Since it can cancel, that means we have a whole when x is 1/2. And so that would be the coordinate point 1/2 something. We'll get to that something in just a second. The other value that made our denominator 0 was negative 3, and that does not cancel top to bottom. Therefore, x equals negative 3 is a vertical asymptote in our graph. Now, in order to find that y value of our whole, I'm going to show that we can cancel this factor 2x minus 1, and then we're left with 2 over x plus 3. So what I'm going to do is plug in the x value of 1/2 into that, since we won't end up getting 0 over 0. So let's plug that in using yellow. So we'll have 2 over x plus 3. When x is 1/2, we'll have 1/2 plus 3. 1/2 plus 3 is going to be 1/2 plus 6/2, so it's 7/2. So it's 2 divided by 7 over 2. That's really 2 times 2 over 7, which is 4/7. So our whole in our graph is at the coordinate point 1/2, comma, 4 over 7. Let's take a look on Desmos and see if we were correct. So we can see on Desmos will definitely show us the vertical asymptote, which we do have at x equals negative 3. That's pretty cool. Now we're not able to see the whole. However, the coordinate point 1/2, comma 4/7 would make sense because here is 1/2, comma 4/7. 4/7 is just a little larger than a half, and it's not like we were way off on the y value or anything like that. We didn't get a y value of like 7 or something. That doesn't make sense. So the whole would definitely be here. Again, a whole is so infinitesimally small that you're not able to see it on the graphing calculator because a point is so tiny. Okay, the first example was way more difficult than the second, which is kind of cool. So if we look at g of x in number 2, we're going to factor both the numerator and the denominator. And actually, the numerator can't be factored at all. It's just one term, so I'm just going to leave it be. In our denominator, we have the GCF of 3, and then we're left with x plus 2. X plus 2 cannot be factored any further, and so we see that if we wanted to, we could now cancel the 3's top to bottom. That doesn't really do too much for us because 3 does not have an x in it, so it's not going to provide us a whole or anything like that. If we look at our denominator, the only value that makes the denominator 0 would be negative 2. And since there's no x plus 2 to cancel with up top, this x equals negative 2 provides a vertical asymptote. So we have a vertical asymptote at x equals negative 2, and we actually do not have any holes in this graph. Since there's no other value of x that makes our denominator 0, that can cancel top to bottom. Again, the 3's can cancel. However, the 3 does not make us equal to 0 ever, since there's no x involved in what could cancel. So That's pretty cool. You could definitely put this on Desmos and see that you do definitely have a vertical asymptote at x equals -2. In conclusion, to find vertical asymptotes and holes, you want to factor both your numerator and denominator if possible. Then you want to identify any x values that make your denominator equal to 0. If that factor doesn't cancel, top to bottom, then the x value from that factor ends up giving us, that's where we have a vertical asymptote. If the x value that makes your denominator 0 comes from a factor that does cancel top to bottom, then there's a hole in the graph there. And that is the x value of the hole. You can find the y value of the hole by plugging it into the factored and canceled polynomial or rational function that you have created from canceling. And as always, you can always check to see if you are on the right track by taking a look at Desmos or a graphing calculator. And just remember that while the graphing calculator or Desmos can definitely show you a vertical asymptote, it cannot show you a hole because they are very small.